This is the second video in our Chapter 4 Oxidation Reduction Reaction set. And in this video, I'm going to talk about oxidation numbers. So this is a way that we can keep track of where the electrons are going. And also we can see which atoms are playing a key role in the oxidation reduction reaction. And so oxidation numbers are the effective charge on a given atom in a compound or molecule. So if you recall from chemistry, many things have a charge associated with them when they're an ion and such, but not really the molecule. But what we're doing within a molecule or compound is kind of using the idea of electronegativity to assign electrons to an individual atom within a molecule or compound. And so these are 4 simple rules that we'll follow, and they will help us determine the oxidation numbers for atoms within a chemical equation. So first, atoms in the elemental state will have an oxidation number of 0. So here, both of these oxygens in O2 have an oxidation number of 0, effectively no charge. Same with copper metal or potassium metal, hydrogen gas. So elemental state, oxidation number of 0. If you have a monatomic ion, so just one atom that has a charge, the oxidation number is that charge. So potassium ion at +1, its oxidation is +1. Oxygen as oxide, -2, and so on. Third rule, hydrogen in a compound will always be +1. That is going to always be the case in this class. I do like to mention exceptions. Sometimes hydrogen is in the form of hydride. This is common in batteries and such. It actually has an electron associated with it, ready to give it to some other species. But in all cases in nature that we're going to deal with, we're going to give it a +1. So say in water, both hydrogens have an oxidation number of +1. Last, number 4, oxygen in a compound is -2. So we will use that in this class. There is a common exception though, peroxide. Peroxide is reactive because it has an oxidation number of -1. But again, we won't use that in this class. We will use these rules primarily to get the oxidation numbers we know, such as oxygen, hydrogen, elemental state compounds, and reactants and products. And then from there, we'll be able to figure out what the rest of them are. So there's obviously lots of elements that we did not mention in these 4 simple rules, but I'm going to show you how to use them. Note too that the total sum of the oxidation numbers of all the atoms is equal to the charge on the compound or molecule. Another note is you should be able to use the periodic table to figure out some of the charges on atoms. We should know that if you're in the first row here, alkali metals, they all have a +1 charge. The alkaline earth metals are all +2. We could also come up with some very common charges, such as the halogens. A lot of times they're -1. Oxygen and sulfur, a lot of times -2. However, not all the case, because again, Sulfur, for example, is very redox reactive. It can have many different charges. The same goes for nitrogen. There's other metals in here that have very common charges. And you can find these in the nomenclature handout and problem set that I have on Canvas. And so a lot of these have very common oxidation states that hopefully you will become familiar with, such as iron +2 +3, copper +1 +2. And so there's quite a few of them, too many to list, but check out that problem set on nomenclature, and it has a table showing common oxidation numbers. And so let's use these rules to figure out the oxidation numbers for atoms within some compounds. And so let's do this first row here. So we have ammonia, we have carbonate, and I have sodium sulfate. So what are the oxidation numbers for each of the atoms? Well, using the rules, we know hydrogen, oxygen, and oxygen. So from there, we're going to use that information to figure out the rest. And so for nitrogen here, we notice that this molecule has no charge. So remember, all the oxidation numbers add up to the charge on the molecule. So if I have 3 hydrogens here, that's +3. That's +3. So that means nitrogen needs to be -3. That balances out. 1 nitrogen at -3, 3 hydrogens at +1 equals 0 if we add those together. So what is the charge on this carbon? Well, we have 3 oxygens at -1, so that's a -6. But remember, this has to add up to -2. We have 1 carbon, so what is the charge on that carbon? +4. +4 plus -6 is -2. And last, sodium sulfate, we have 2 unknowns, at least it seems. But you know from the periodic table, sodium being an alkali metal, it has a +1. And so if all of this equals 0, we have 2 sodiums, we have 4 oxygens, so this is a -8 total. This is a +2. What is the charge on sodium to give me a 0? +6. So you should be able to do this for different compounds. Note too, common mistake, oxidation number for oxygen is -2. Sometimes students put down -8. That is incorrect. I know there are 4 oxygens at -2, but you need to put the appropriate oxidation number for a single atom. So let's do these ones on the bottom. What do we got? Well, we can fill that in. We know using the rules, we know what hydrogen is, we know what oxygen is. And so manganese here, what do you think? Should we do, let's just do the math real quick over here. It's going to equal 0. So this is a -4. So that means manganese must be +4. Carbon here, well, there's 4 hydrogens at +1 each. So in methane, carbon has a charge of -4. It is in a reduced form, we'd say, especially compared to something like carbonate, where the carbon is actually +4. So this is in a oxidative state. And last, this iron, well, if we have 3 hydrogens, 3 oxygens, and so we have a +3 here. We have a -6. We add up 3 oxygens at -2. They all add up to 0 +3. So again, you should be able to do this for different compounds and molecules within redox reactions. So one application to this is just to kind of be able to follow what's going on in a redox reactions. So many of the important redox reactions in nature are performed by microorganisms. And the reactions that are important that they completely own are those that are thermodynamically favorable. That means they can happen on their own. If you just look at the products and reactants, it's obvious that they are spontaneous, but they are reactions that are extremely slow in terms of their kinetics. Just for example, how about the oxidation of wood or any kind of cellulose? That is respiration. That is this reaction here where you have biomass, you react with oxygen, and you make CO2 and water. That's what happens in a campfire. But does a piece of wood just turn into CO2 and water? It does not. It takes very long time. It is a kinetically complex reaction. And what it takes is organisms, microorganisms, or even us in our cellular processes during respiration to make this happen. And so we're primarily talking about bacteria, actinomycetes, which are in the soil, fungi, algae, and protozoa, all the small critters that make our world a better place. And so let's look at aerobic degradation. It is favorable. We look at the sign of delta G for this reaction. It's negative 502 kilojoules. And again, they have supplied a pathway in order for those reactants to turn to products. And so we can break down each reactant and product and look at the oxidation numbers and figure out what's going on. When we do so, we see that the carbon in the biomass has an oxidation number of 0, and it turns into a product of carbon dioxide that has an oxidation number of +4. So we can see that what occurred here is that the biomass became oxidized. It became oxidized during this reaction. And oxygen, we have O2, oxygen in the elemental state, therefore its oxidation number is 0, and it's converted to water, where oxygen has a -2 oxidation number, therefore this is where it became reduced. And so again, we can follow now which is the oxidizing agent and which is the reducing agent. So which is the oxidizing agent and which is the reducing agent? So let's start with the reducing agent. The reducing agent is something that becomes oxidized itself, but reduces something else. So that means that the reducing agent is the organic matter. This is the reducing agent. And oxygen, gas, as the name implies, is the oxidizing agent. It oxidized something else. It oxidized the dissolved, or excuse me, the organic matter, but in result, it reduced itself. So last one, let's look at anaerobic degradation. So this occurs when there's no oxygen around. And what we have here is organic matter reacting with itself. So in actuality, it oxidizes and reduces itself at the same time. Again, this occurs in the presence of microorganisms. And it is also negative. So remember what this means. It means it's spontaneous, but it also means that the microorganisms can get energy out of this process. That is what they're interested in, right? They want a process that actually can help run their metabolism. So they're interested in kinetically slow reactions that they can mediate, that they can take control of, but they want ones that can actually supply energy. And so in this reaction, we form a product that is reduced and a product that is oxidized. We would also have to say that the oxidizing agent and the reducing agent are both organic matter. So this just kind of gives you a different look. They're not all completely straightforward, but I think you can figure it out.